All right, this second video is going to take you through the catalog of forces. So these are all the different types of forces so that when we label a force diagram, we give it the correct variable and we can kind of understand who the agent of the force is, because that will help us identify the forces. So the first force is kind of a general catch-all force. It's like a general or applied force. Basically, this is any push or pull that does not fit in any of the other categories I'm about to describe. So the variable that we use for this applied force is FP. Sometimes you will see F sub A. Either is acceptable. There's no real required. The agent of the force is just whatever is exerting the force, so the exerter of the force. You could also call this the agent of the force. Okay. So the direction is along the line of the force here. So if I have a man in this picture right here who is pushing on the ice cube, and this ice cube is my system, then the direction of that force, if I drew a dot here, would be along the line of that force, and I would label that as the applied force. So dot, shrink down your particle to a dot, that's what I'm interested. The force starts and touches on the dot and is drawn away. Okay, the normal force. So the normal force is one that comes up all the time. The normal force doesn't mean not strange. The normal force actually gives you a direction of force, and it is really perpendicular. The normal is due to a surface. That is the agent of that force, and it acts perpendicular to the surface. So that normal force is F with a capital letter N as a subscript. That would describe the normal force. So if I looked at box B, if box B was the system that I was interested in, okay, there's going to be a support force from the surface due to the floor itself. So this would have a normal force directed upward right there. And again, I drew it touching the surface here just to kind of indicate the two different forces, and then I'll draw how it would look a little bit over here. I'll draw the dot over here. So this is the point of application of the force. It's coming from that surface and acting upward. So that would be the normal force on box B by the surface, by the floor. And then box B is also providing a surface right here. So box A is pushing on box B that way. Let's say my whole system is maybe moving this in this direction. So that's our velocity vector. So this would be another normal force, and I would draw it like that. And that would be the force on box B by A. And this would be by the floor. So they all have the same object, box B, but the agent is caused by two different surfaces. So that's the normal force. Friction is a resistive force. Between surfaces. So again, the agent is going to be the surface itself. So when you see some surfaces, there are two possible forces that may be applied. You could have either the normal force or the frictional force. So you have two forces that are due to surfaces. The force of friction has two different styles we're going to talk about. So in general, any kind of friction force is capital F with a lowercase f, but we have kind of two different types of frictional force. One is sliding. So actually the two surfaces are moving relative to each other, and this is called kinetic friction. And the symbol for kinetic friction, sometimes you'll see it simplified again just with the lowercase f and then a sub k for that, for kinetic friction. And then static friction is when something doesn't slide. So there's no sliding. An example of that would be if I put a box on a ramp and it didn't move at all, so the speed is 0. What's keeping this box from sliding down the ramp? That would be friction. Friction is holding it up. Okay, the direction of this force is going to act opposite the motion or the intended motion. And I'll explain that as well. So for this case, we have a box that's moving to the right with a velocity v. So if it's moving to the right, then friction is going to act to the left. That would be my kinetic frictional force. So if I was drawing this box and just drawing the frictional force, it would act opposite that motion. But the point of application, like where the contact of that force is, would be the box. But a force diagram, we're just going to draw our dot, and friction would be to the left. Okay, static friction. So if my box is not sliding, the intended motion is to go down the ramp. But friction, again, is preventing it from sliding down, and that would be static friction. So no sliding or no movement is called static friction, static. And the symbol for static friction is lowercase f with a sub s. So this would be static friction. And again, if I drew my dot right here, my direction of static friction would be parallel to the ramp, parallel to the surface, but directed opposite the motion. So kind of along the line of the ramp angle itself. So these are probably three of the most important: the normal force and the frictional force. So those two, and then static and kinetic friction. All right, tension forces. Tension forces are due to ropes or strings or wire. So the agent is really the definition. So this is the force. Oops, I'm doing it in the wrong place. Let me fix that. Okay, this is force. There we go. Force due to a rope, a string, or anything like that, maybe a wire. Okay, the direction is going to be along the wire, and the symbol that we use is F with a capital T as the subscript. So here we have, again, another box that's being held up by a rope right here. So if I were to draw this force diagram, I'd start my force at the object of interest, and I draw it along the direction of the force, away. So the tension force is holding that box up the ramp. But again, it would be at an angle, and just along the same angle that I would do, and that would be my tension force. Okay, spring forces are a very special case of forces. F sub SPR, usually to kind of differentiate it from a static frictional force. The agent of that force is going to be the spring. The spring pulls on it, much like a rope pulls or pushes on something. So if this was my object that I'm interested in, that spring force is going to act along the direction of the spring. So again, if I kind of simplify my box to just a dot, I would draw the force of the spring going along the action of along the direction of the spring itself. So spring forces have a lot more detail. We'll be spending a lot of time talking about spring forces in this unit and the coming units. All right, just for completeness, drag is another type of resistive force, but this is due to a fluid like air or water or oil or something like that. Sometimes we just use a capital letter D to indicate the drag fluid, the drag force. The agent of that force would be the fluid itself. And then we're going to do this drag and the thrust force all on our same diagram of the rocket that we see below here. Thrust force is like a propelling force. We've done some examples with rocket engines in our acceleration unit. So that would be FTHR for thrust, or anything that seems really. The agent of the force is the propellant that is ejected from the engine. And when we get together, I'll demonstrate a fan cart. So I'll try to remember to demonstrate the fan cart when we get back together again with the thrust force. So if this is my rocket is my object that I'm interested in. The gases down here are going to push the rocket upward. So you're going to have your thrust force that way. And then air resistance is going to act opposite that motion, just like a frictional force. And I might have a drag force acting opposite that motion. And that would constitute the thrust force that you might run into as well. All right, so these classes of forces, these are all, as I mentioned, contact forces. They were easily identified because we knew what was touching the object. You kind of just look at your picture and ask yourself what is touching, and they become contact forces. Strictly speaking, all of these contact forces are actually electrostatic forces. Basically, these resist the forces that are pushing objects or friction, all of these things, tension forces. They're really an interaction on the molecular level of the bonding nature of electrons and protons. But if we called everything an electrostatic force, it would get kind of confusing. But in its essence, all contact forces are, in fact, electrostatic forces. All right, moving down here. The last remaining class of forces are the non-contact forces. And again, this is where you cannot see the agent of the force. Nothing is touching. And as I mentioned before, the first one is going to be the force of gravity. That is going to be our number one important one that we'll be dealing on it. This is the pull of an object. An object when placed in a gravitational field. And a gravitational field is think of it kind of like a magnetic field. Like, so when you have a field around a magnet, and if you place something that is metallic or near it, or magnetic near it, it will pull or push away from it. So think of that magnetic field similar to a gravitational field. The other name, and I'll do some demonstration with that as well when we get back together, the other name for the force of gravity is also known as, AKA, the object's weight. So the weight of an object is the force of gravity on the object. So you will see F sub G for the force of gravity, or sometimes you'll see a capital letter W for the weight. The agent of this force is the object's gravitational field. Well, I shouldn't use the word objects. Let's use the case that we're going to be most using, and that would be the Earth. So the Earth's gravitational field. But this could be any planet. And as we will learn later, actually any object with mass has its own gravitational field, but we'll focus on the planet's gravitational field. The direction of this force is going to be down towards the center of the planet. That is the main one. That really constitutes all the forces that we're really going to be discussing. The other two, just for completeness, are the electrostatic. And this is not like talking about the contact forces, but this is actually like when we see static electricity and your hair flies up, that electrostatic force, and then magnetic. And we won't really talk much about those at all. Okay, big difference between these forces. These forces here will be pushes or pulls. But gravity is kind of different in that it only pulls. So it will only pull, and there's one big difference between those two. All right, before I give you your assignment for this, just identifying the forces, and we've been doing this, or I have been doing this as an example, to kind of help you identify. So again, ID your system. What is the object that I'm interested in? You'll see forces acting on them. You'll identify pushes or pulls. You'll look at contact, non-contact forces. How we define our system is very important, because sometimes I might be interested in the AB system, and C would be an agent of forces. And we can see that kind of demonstrated out here. So we can and will redefine our system. Sometimes we're just interested in object A, but sometimes we want A and B. Sometimes we want A, B, and C. So we'll treat this from a lot of different perspectives. Draw a circle around the system. Everything that crosses the circle from the outside is an agent or a contact force, and you identify it from the list that was given above. And then gravity is the only non-contact force, and it's always there. So you can always put the force of gravity in there. All right, as I mentioned, we talked about drawing the free body diagram, represent the system with a dot. We've done that, kind of simplify it. It's that particle model. Label and draw all the force vectors for the contact forces. If you cannot identify the agent of the force, guess what? It's probably not a force, so keep that in mind. And then draw and label the force of gravity. It's always down unless it's some kind of space-based problem, and then that would be a little more challenging. All right, so what I'm asking you to do as your assignment is to fill in all of these force diagrams, and I'm going to do one as an example for you. So the box is at rest on the table. The box is going to be my system here. So the box is the system. So I'm going to draw my dot here to represent my system. I have a surface acting upward. That is going to be due to the surface itself. That is a normal force. I have nothing else that's touching my box. It's not sliding or has any potential to slide, so there's no static friction here. And then, of course, there's going to be the force of gravity acting downward. Okay, so if it's at rest, think about mechanical equilibrium. We talked about whether the forces should be balanced or unbalanced. I know that this system's in mechanical equilibrium because it's at rest, so I know that these forces must be balanced. So what that tells me is that this force is going to be equal to that force. Okay, so I'm going to ask you to go through all of these examples, 1 through 17, and recreate the dot for each one of them and draw and label all of your systems.